Good day, grade 11s. All right, so today we'll be looking at Euclidean geometry, right? All the 9 theorems. So if you haven't subscribed, please just make sure that you're part of the family, right? So we're going to take it slowly. You can play this video at 2 times the speed if you want to. Okay, so let's just look at all the theorems. All right, let's start with theorem 1. So if we look at theorem 1, the first theorem tells us if we've got a line that is drawn from the center, so if we've got a circle and we draw a line from the center and that line is perpendicular to the chord, right? Please note that a chord is a line that moves from circumference to circumference. Okay, so we say that if a line is drawn from the center and it is perpendicular to the chord, then we know that it bisects that chord, right? So let's suppose that we've got line O, center O, and we've got chord AB. All right, let's say that it reaches, the line reaches the chord, in this case at C. Right, so if that line from the center is perpendicular to the chord, remember perpendicular means it forms a 90 degrees, then we say that it bisects the chord. So what is our, what are we given? We're given OC perpendicular to AB, right? And our conclusion, therefore, is that if that line is from the center, which is O, the center of the circle, therefore we know that in this case, AC will therefore be equal to CB. All right. Now note that theorem 1 also has got a converse, and I'm going to give you an easier way to state that theorem. In fact, I might as well do that. So when you state the reason, in this case, we always say line from center. Okay, so this is line from center perpendicular to chord. Okay, that's the reason. Now, if we draw again, so suppose that we've got our chord, and we draw a line that is from the center. Let's suppose, okay, I know my center is not really nicely centered. Okay, so let's suppose in this case that we've got, again, center O, we've got AB, and now we are given that AC is equal to CB, right? So note in this case, we can say, well, a line that is drawn from the center that bisects a chord is perpendicular to that chord, okay? Notice in this case, what are we given? We're given that AC is equal to CB, right? So meaning that chord AB is bisected, okay? So therefore we can conclude that it means that OC is therefore perpendicular to AB. Now note, how do we state this reason? In this case, we say that this is the line from center. This time we say bisects the chord. All right, so that is how we're going to state theorem 1. Right, very easy. And please note the first 3 theorems rather have to do with the center. Right, now let's look at the second one. Right, so theorem 2, okay, as we swiftly move along. Now, what does theorem 2 state? It simply states, again, it has to do with the center, that if we've got a line, in this case, if we've got center O, all right, it simply says the angle at the center will be equals to 2 times the angle at the circumference. So supposing that we've got a center, which is O, right, now let's give the name there. Let's suppose that this is A, this is B, and this is C, and that is our center, which is O, right? So now what does that mean? it means that angle AOC is equal to 2 times angle ABC. Okay, so now I want to state this very clearly. Supposing that, let's say, this angle here is 40 degrees. I'm just making an example, right? So what does that mean? It means the angle at the center will be 2 times that number, so which means this angle will be at 80 degrees. Now please, two things that you must make sure: that O is definitely the center, and that B must be at the circumference. If it is not at the circumference, therefore you cannot use this theorem. Right, I just want to show you other ways in which we can do this. Right, now when you give the reason, we always say angle at center equals to 2 times the angle at circle. Okay, yeah. All right, so that is the reason. Now, note other ways in which they can show you this theorem, right, is that we can actually do this, and very deliberately so, they can give you the line. Let's say this is, again, this is O, all right? Now, they can draw it in this way, right? Now, it doesn't look very obvious, but note, once again, you've got the line at center, right, or angle rather at center, which is this guy over here in red, and the angle at the circumference, so it reaches the circumference over there. So now we know that if we said this is B and C, then again ABC, or rather AOC, is equal to 2 times angle ABC. All right, let me write that nicely. So 2 times angle ABC. Right, there's another way again, so you can actually get this as an obtuse angle at times, right? So there's our center O. So if we draw that as, okay, firstly, you'd have a reflex angle over there. So supposing this is our center O, right? So if I give you that angle over there, right, and we say, let's suppose this is O, center O1, and again we've got A, we've got B, and we've got C, right? Once again, which means that angle AOB, now note I'm talking about the one that is on the outside, right? Or we can call it O1. So which means O1, angle O1 is equal to 2 times angle, okay, let's say angle ACB. All right, so please note angle at center is equal to 2 times the angle at circumference. So if this was 120, that means angle O1 would therefore be equals to 240, which is twice that. All right, now let's move on to the next one, which is theorem number 3. Right, so how do we state theorem number 3? As I said to you, the first 3 theorems have to do with the center, right? Now, theorem number 3 kind of looks like theorem number 2. So this simply says, right, if a line, or rather if an angle is subtended by a diameter, that angle is equal to 90 degrees. Okay, so I know my lines are actually not as accurate as they should be, right? So if we say this is ABC, right? Notice if I say to you that AC is a diameter, right? Now remember, what is a diameter? It is a line that cuts the circle into 2 equal parts, right? Or you can say that it is a chord that divides the circle into 2 equal segments, right? Now I want you to please note, if AC is a diameter, therefore it means that angle ABC, right? So angle ABC is equal to 90 degrees. So meaning this angle over here would be equal to 90 degrees, right? And how do we state the theorem? Well, we shorten it this way. We simply say angle at semicircle, right? So note that when we say semicircle, remember we did say that this would be a diameter which cuts the circle into half, right? So in this case, we simply say this is the angle at semicircle, right? What I want you to also appreciate is the fact that it actually kind of looks like the previous theorem, isn't it? Because think about it, what would be the size of that angle there, right? It would be 180 degrees. So angle at center twice angle at circumference. 90 times 2 gives us 180, right? So remember, this is angle at semicircle. Now, we're done with the first three theorems. Right, now let's go to theorem 4. So the next batch of theorems have to do with, now note in this case, let me just remove that line, right? So the next batch of theorems have to do with the cyclic quad, right? So theorem 4, I want you to please note, how do you state theorem 4? Right. So if we've got a circle, now what is a cyclic quad? It is a four-sided figure whose vertices touch the circumference of a circle, right? So let's say we've got a four-sided figure there. That's A, B, C, and D. Right, now the first, theorem number 4 simply says that the lines, or rather the angles that are opposite a cyclic quad are supplementary, right? So the opposite angles of a cyclic quad are supplementary, meaning if I take angle A plus angle C, right? So A plus C would be equal to 180 degrees, right? Note again, so it means D plus angle B would also be equal to 180. And how do we state the reason there? We simply say opposite angles of a cyclic quad. You don't need to tell us what that means, right? But we know as soon as you say opposite angles of a cyclic quad, then we know that they are supplementary, which means that they form 180 degrees, right? Now, the second one that has to do with a cyclic quad, right? So that's theorem number 5. Right. Now, what does theorem 5 say? Right, again, it has to do with a cyclic quad. Okay, so which means in this case, all the four vertices, right, touch the circumference of the circle. Now note, the moment that they tell you, suppose that I gave you this line and I say this is AB and I say this is CDE. Usually, when they say something like CD is produced till E, what are they trying to tell you? That forms a straight line, right? So what we say there is that the exterior angle of a cyclic quad, notice it is the angle outside the cyclic quad, is equal to the opposite interior angle, right? So this angle here, which is on the outside of the cyclic quad, right, would be equal to the opposite interior angle. Right, now please, I want you to note, ladies and gents, that once we use this theorem, right, so note that how do we state this? We just simply say exterior angle of a cyclic quad. Okay, right. All right, I couldn't fit that all in there, right? So the exterior angle of a cyclic quad. So we know in this case that that is definitely equal, right? All right, so which means if we look at angle BDE would be equal to angle CAB. Right, and that is the angles that have to do with the cyclic quad. Now, guys, I want you to please note, as we move on to theorem 6, right, we're almost done. So, anytime they want you to prove that an angle, or rather something is a cyclic quad, a four-sided figure is a cyclic quad, which means you must use any of these theorems, right? So which means if the opposite angles are supplementary, therefore it's a cyclic quad. Or if the exterior angle is equal to the opposite interior angle, then it means that it is a cyclic quad. And then theorem 6. Right, now theorem 6 has to do with angles subtended by the same chord, right? So if we note in this case, let's suppose that we've got A, B, C, and D once again. Right, now note we say these are subtended by the same chord or they are subtended by the same arc. I'm going to show you which one is the chord here. So imagine there's an imaginary line that is there that I've drawn, right? Or another imaginary line there. So you can either use that imaginary line or you can say, well, here is we call this an arc, right? So an arc is a part of the circle, right? So we've got another arc there at the top. Okay, I'm going to draw it in a blue color. So there is another arc over there. Now notice we say that the angles that are subtended by the same arc are equal, right? So meaning angle A would be equal to angle B, right? Let's write it nicely. So they say in this case we've got DAC, angle DAC will be equal to angle DBC. So that angle there is equal to that angle, or you can just simply say angle A is equal to angle B. Now note, what do you say? Right, the reason that we give is that we always say angle at same segment. Okay, we would definitely understand what you mean when you say these are angle at same segment, right? Now, note once again, it has to do with the cyclic quad. So meaning if I can prove that angles at same segment are supplementary, then it means it is not supplementary, rather, they are equal. Then it means it is a cyclic quad, right? But once again, look at this. We have another pair of angles at same segment, right? So this guy here should be equal to that guy over there, right? So those blue angles over there. So which means angle D is equal to angle C, okay? Or you can say ADB, right? So that's ADB is equal to angle BCA. So BCA. So remember BCA would be that angle over there. Right, once again, why? Because angles at same segment are supplementary. Now, please be very careful, ladies and gents, that it must be touching the vertices of the circle, right? If it doesn't, then they might say to you, you must prove that it is a cyclic quad. And if you can prove, right, we're going to do lots and lots of questions on these proofs, right? So in this case, it means that if you find that it is the case, then you can conclude that it is a cyclic quad. Right, now, ladies and gents, some may not be very popular. In fact, let me just continue using the white. Okay, so what we can also do on this one is that we can also say that angles that are subtended by equal chords are also equal, right? So if I give you, suppose I say to you, okay, I've got a chord there, right? Okay, so if I tell you that, let's say this is going to be A, B, let's say C, let's say this is D, E, and F, all right? Now I want you to note, if it is given to me that BC is equal to DE, it is given. So given that BC is equal to DE, right? Please, I want you to note, so I've got equal chords there. So therefore, I want you to note that the angle that is subtended by those chords would therefore be equal. So meaning angle A, so therefore it means angle A would be equal to angle F. Or you can say BAC, right? So that's BAC is equal to angle DFE. So that's DFE, like that. All right, and by the way, how do we state this? We say these are angles, okay, that are subtended by equal chords. Right, so I want you to please note that. Now, ladies and gents, let's go on to the very next one. Right, another way in which they can use this, okay, not very popular as well, but it can be used. So supposing again that I've got a similar situation, right? So let's say, okay, my lines are not behaving. All right, let's remove that line. Okay, so suppose that I say to you, there it is there. Right, so I want you to note, ladies and gents, if I were to give you that scenario. Now note, suppose this is given to me as center O again. So there's my center. Let's say this is going to be A, B, and let's say this is D, E, right? Now note, if it is given to me that AB is equal to DE. Now please, guys, I want you to note again that it means that this angle here would be equal to that angle over there, only on condition that that is the center, right? Now note, those are not vertically opposite angles, right? So we can say, right, given that AB is equal to DE, therefore we can say that AOB would be equal to EOD, right? And why is that? Once again, these are angles that are subtended by equal chords. Right, so by the way, ladies and gents, this is not a very popular one, but it does appear now and then, okay? Right, and now we go to the very last three, right? So let's go to theorem 7. So we are done with the ones that have to do with the cyclic quad. Now we look at the ones that have to do with tangents. The next three theorems have to do with tangents, right? Now the first one, let's talk about the very first one, right? And it simply says, if I've got a tangent that is drawn, right, a line that is drawn from the center will be perpendicular to the tangent at the point of tangency, right? So meaning I'll have a 90 degrees there, right? In this case, if we've got, let's say, O, let's say that is our line A, B, C, right? So if I know that OB is definitely the radius, and in this case, AC is the tangent to the circle, then I can conclude that therefore OB is perpendicular to AC. Now we simply call that the tan radius theorem. Tangent perpendicular to the radius. Just simply put like that. Okay. Right. Now remember, what's a tangent? It is a line that touches the circle only once. Okay. Right. Now let's go on to the next one that has to do with the tangent. Okay. So, right. So if we get, again, we can take line that is a tangent. So this one simply says that if I have tangents that are drawn from the same point outside the circle, those tangents would be equal. Now please guys, I want you to note, supposing that I know this is going to be, let's say A, let's call this point P, let's call this B. Now from the point of tangency till point P, which is a common point, from the point of tangency again, which is A, till point P, which is a common point, then it means that AP is equal to BP. These are called tangents from the same point. Okay, right, so these are tangents from the same point. Right, so there we go. Now please, I want you to note guys, the moment you start having equal equal sides, if I had to do this, please, I want you to note, the moment I start having equal sides, if I were to do this, then what type of triangle would APB be, right? That would be an isosceles triangle. And what do I know about an isosceles triangle, right? The base angles of an isosceles triangle are equal. But we're going to talk about all of that, right, once we start, delving into Euclidean. For now, I just want you guys to master these theorems and know them off by heart. All right, now let's go to the next one, right? Tangents from the same point, we know that they are equal. And the last one, the very, very, very last one. So in this case, if I have got a tangent, okay, right, I don't need to have a center there. So let's draw our tangent. Okay, so there's the tangent. So we know that a tangent, or the angle between the tangent and the chord, will be equal to the angle that is opposite that chord, right? So we call this the tan chord theorem. Now suppose this is our tangent ABC, right? And let's say this is D and E. Right, I want you to note guys, it means that if I were to take this angle over here, right? So there's my tangent, there is my chord, the angle that is opposite that chord, which is that guy over there, would be equal to that angle there, right? So we call this the tan chord theorem. So therefore, it means that I've got angle DBA. So angle DBA would be equal to angle DEB. And we say that this is the 10 chord theorem. And I can tell you this, ladies and gents, there is absolutely no way that they will never ask the 10 chord theorem. It's one of the favorites with examiners, right? So meaning, in the same token, that this angle over here, right, there's our tangent, that's our chord, so which means it would be equal to the angle on the opposite side of that chord. So there it is once again. So I can say that EDB is equal to EBC. Right, and that we call the 10 chord theorem. And please note, ladies and gents, once again, if they want us to prove that something is a tangent, which means we're going to use the converse of any of these three theorems, right, to prove it. Okay, right, so that is how the cookie crumbles, ladies and gents. Now, what we're going to do next is I want to show you how to apply these. What's the first thing that you do when you encounter any questions on Euclidean geometry? All right, but we will do that on our next video. Otherwise, for now, please see our next video and do enjoy. I'll see you next time. Sharp, sharp.